we are now down to the last illustrious speaker, and Professor Milind Tambe. Requesting, he's ahead of me. He's already shared his screen. So let me introduce our last speaker, and this is going to take a while. So Professor Milind Tambe is the Gordon McKay Professor of Computer Science and the Director of the Center for Research in Computation and Society at Harvard University. Concurrently, he is also the Director of AI for Social Good at Google Research India. He is the recipient of the IJCAI John McCarthy Award, the ACM SIG AI Autonomous Agents Research Award, AAAI Robert S. Engelmore Memorial Lecture Award. He is also a fellow of AAAI and ACM. For his pioneering research in real-world deployment of security games, Professor Tambe has received the Inform's Wagner Prize, the RIST Prize of the Military Operations Research Society, the Christopher Columbus Fellowship Foundation from Homeland Security Award, as well as commendations from the U.S. Coast Guard, LA Airport Police, and U.S. Federal Air Marshal Service. Additionally, he and his team have received over a dozen influential paper and best paper awards at premier artificial intelligence conferences. Professor Tambe received his PhD from the School of Computer Science at Carnegie Mellon University. Thank you for joining us, Professor Tambe. Please take it away.
Well, thank you for inviting me for this wonderful gathering. And I'm going to speak about AI for public health and conservation. Thank you for that really wonderful introduction. So with the current progress in AI and multi-agent systems, it is now important to direct these advances towards societal benefits. We focused in our lab in 3 areas: public health, conservation, public safety, and security. Today's talk will focus on public health and conservation. In all of this work, the key challenge that we focused on is how to optimize our limited intervention resources when we have agents interacting with other agents. Specifically for public safety and security, we have a large number of targets to protect limited security resources, how to schedule or plan or allocate our resources, taking into account a watchful adversary. We've in the past introduced a new model called Stackelberg security games that have been in use by security agencies in the United States, from the Federal Air Marshals to the US Coast Guard and others. With respect to conservation, we have large conservation areas to protect limited ranger resources. Concrete example that I'll speak about today is work we've done in Uganda and Cambodia. Taking into account past poaching data, we are able to predict where poachers may set traps or snares and have been able to remove a large number of snares and even get poachers arrested. With respect to public health, key challenge is we have large number of beneficiaries, but not enough social workers or public health officials. A concrete example is work we've done with homeless shelters in Los Angeles. Harnessing the social networks of homeless youth, we are able to show that our influence maximization algorithms are far more effective in spreading information related to HIV compared to traditional approaches. More recently, having taken up the role of Director for AI for Social Good at Google Research India, we've launched 6 separate projects, several in public health, with NGOs such as Arman, Kushi Baby, Swasti. Often these have been focused on maternal health and child welfare. In conservation, with NGOs such as Wildlife Conservation Trust and Ashoka Trust. This is for preventing human-wildlife conflict. In education, for translating books into languages, low-resource languages. And more recently, work related to analyzing mobility in COVID-19. I saw an earlier presentation to that effect as well. Fortunately, given the limited time, I'll not be able to speak about much of this work. So I'll focus mostly on the earlier slide that I mentioned, focused on public health and conservation that we've done before I joined Google. So there's 3 themes that you'll see regardless in all of these presentations, in all of these projects. The use of multi-agent systems research, in particular use of social networks and game theory. The idea for data to deployment pipeline being that we start with an immersive process, trying to understand the social problem that we are interested in, understanding what kind of data to collect. Following that, a predictive model informs us, makes predictions about which of the cases, which of the patients are high risk versus low risk. Following that, a prescriptive algorithm, where this is where the multi-agent reasoning comes in, provide some techniques to understand which of the high-risk cases we can actually intervene on. Given that there's a large number of cases and not enough resources, we can't intervene on everything. So which cases should we intervene on in order to have maximum impact? But very crucially, it is very important for us to actually field test and deploy our algorithms in the field. And so when we talk about AI for social impact, it is important that we actually have social impact, and therefore social impact is a key objective of this research. Secondly, throughout this pipeline, you'll notice that lack of data is a norm. We have to be used to the idea that we're not going to be swimming in large quantities of data in these kinds of domains. And so lack of data must be part of our project strategy. A third theme that you'll see throughout is interdisciplinary partnerships. All of this work is only possible because of the partnerships with conservation organizations such as WCS, WWF, with homeless shelters, with different types of NGOs. And to that end, we've really patrolled with wildlife conservation agencies in their forests. Students have spent time in homeless shelters. This kinds of interdisciplinary partnerships is where we get our initial problems, this is how we get to test and deploy our algorithms in the field. So with all of this, I'll start to talk about public health as the first topic. Most of this work has been done jointly with Professor Eric Rice, who's a social work professor. I'll also put pictures of my PhD students and postdocs who've led particular work that I've shown on those slides so that you know who is responsible for that work. So let me start with the challenge we face with HIV prevention amongst homeless youth. I'm talking about the city of Los Angeles here. There's 6,000 homeless youth who sleep on the streets of Los Angeles every night. Preventing HIV is a key challenge because rates of HIV amongst homeless youth are 10 times the rates of normal housed population. Homeless shelters want to spread information about HIV, but we can't go and reach out to every one of these 6,000 youth. So they will find peer leaders, key peer leaders to whom you can give information. And these peer leaders talk to their friends and their friends talk to their friends. And in this way, information spreads in the social network. Now, this is a real social network gathered from observations in the field. This is not electronic network as in Facebook or something like that. This is how people talk to each other. So this is the classic problem of influence maximization that we know in computer science. You have a social network, graph G, and you have to choose K peer leaders to maximize the expected number of influence nodes. We assume that information flows with this independent cascade model. So we take a homeless youth A, we inform A about HIV prevention. We assume there's a probability 0.4 that this node A, homeless youth A, will speak to his or her friend B, and we know this probability is 0.4. And this is how information about HIV prevention will spread from A to B. Immersion in this domain, obviously, it showed us that these probabilities are not known exactly. So if we talk to a homeless youth C, we don't exactly know the probability with which C will talk to D. So we can assume that this probability is drawn from some distribution, but we may not even know the mean of this distribution, and therefore we can assume that this mean lies within a certain interval, as shown here. So now we face this problem of influence maximization with uncertainty over this probability in which information spreads. So this problem we've solved by casting it as a zero-sum game against nature. So our algorithm is trying to choose a policy, choose which peer leaders, whereas nature is trying to choose parameters that cause our regret to be as low as possible. And so you can imagine this is the game. You have an influencer which is choosing different policies. A policy refers to choice of a particular set of peer leaders, particular set of influence maximizers. And then nature is going to choose parameters, which is along the columns, to get the policy to perform as worse as possible. This is the regret that is shown here. Now, of course, this game is very, very large because the number of policies is massive, exponential. Nature can choose a whole variety of parameter settings because it's a continuous range from where we choose. So to solve these kinds of problems, we use a double oracle approach. We start with a small game matrix, and then the influencer's oracle gives us the next best response to add. And then nature's oracle gives us the next best response to add. And in this way, iteratively, we grow the game matrix until we reach equilibrium. And we can show that this equilibrium strategy converges with approximation guarantees provided, even though nature strategies are selected from this continuous interval. So this is how we can build a robust influence maximization strategy. There is, however, a second problem that we must address. We want to, let's say, select 12 homeless youth in a group of 60, inform them about HIV prevention. We cannot get all 12 to show up simultaneously. We just don't have the capacity to educate all 12. So we may choose only 4 youth at a time because that's our capacity. Now, these youth are in unfortunate circumstances. So we may invite youth A, B, C, D, but youth B might get arrested and some other person may show up. Another youth might decide to run away. And so the people who show up may not be the people who we invited and may not be all 4 that show up. So we have to then, when we call the next group of 4 youth, compensate for the fact that a different group showed up in the first round. So this is a problem of planning under uncertainty, and this can be solved as a POMDP. And so we now have a choice of selecting a group of 4 youth in each round, but we are going to choose this using a POMDP policy. Of course, POMDPs are hard to solve notoriously. And so there are some decomposition strategies, partitioning strategies that are used to solve these POMDPs. So with this now, we have this healer algorithm in place in order to solve this problem of influence maximization, choosing homeless youth to spread information about HIV. So now comes the part of us going to homeless shelters, actually doing this work with actual homeless youth. This is not a simulation. We recruited homeless youth in 3 different categories. Healer and Healer Plus are 2 different algorithms, one using the POMDPs, one using a more greedy algorithm, but both using this game theoretic approach that I mentioned. Degree centrality is the traditional approach. This is the one which homeless shelters use, bring in the most popular youth in order to spread information. So we recruited 60 youth under each category. 2 our algorithms, Healer, and 1 is the traditional approach. We selected 12 youth in each case as peer leaders. Then our colleagues from School of Social Work educated these youth about HIV prevention, as shown in this picture here. And then after a month, we want to check who is able to spread more information, whether it's our AI algorithms or it's the degree centrality, the more traditional approach. And here's what we find. Healer and Healer Plus cause 75% of those who are non-peer leaders, those who we did not bring in to provide HIV information, to be informed. With the more traditional approach, only 25% of those youth got informed. In other words, at the end of a month, we had a much larger category, much larger fraction of the non-peer leaders informed by using of our AI algorithms. But of course, one big challenge here is that we needed to collect the social network of this homeless youth before we were able to use our algorithms. This data collection is costly because social workers have to go in the field and observe which youth is talking to which other youth. To prevent that, we decided with a newer approach where we only sample 18% of this network. So we sample a small fraction of this network and then run our influence maximization algorithm. Our first approach was to sample from the largest communities, which provides theoretical guarantees. In practice, this approach turned out to be less effective. Therefore, a simpler sampling approach was used, which relied on the friendship paradox. And again, in simulations, everything works well, but in practice, in the real world, how well is this going to work? So again, we recruited 60 homeless youth, again, recruited 12 peer leaders using our algorithm. And then the question is, can just sampling 18% of the network work as well as knowing the entire network? And the answer is yes. In fact, even though we sampled a small fraction of the network, still 80% of the non-peer leaders got informed about HIV. So this gives us a lot of hope that the sampling algorithm really works in practice. Okay, so these were all pilot tests. How is this going to work on a large scale experiment? And so for that, we have recently completed results. This is in collaboration with Professor Eric Rice, with 800 homeless youth in 3 different homeless shelters in Los Angeles, My Friend's Place, Safe Place for Youth, and Los Angeles LGBT Center. And in these, we tried 3 arms. One is our sampling algorithm for spreading HIV information. Second is the normal degree centrality approach. And the third is a control arm where no intervention was tried at all. And then we tried to look at actual behavior change, not just information spreading, but what was the change in behavior. And we see here with the sampling algorithm and doing influence maximization, there's a significant reduction in condomless anal sex, which allows us to show that this degree centrality or control approach is quite inferior to using our algorithms in order to spread HIV prevention information. We also did a test at the end of 3 months to see how well that performed. And with degree centrality started to catch up, but still it's not as good as sampling. And of course, the speed at which this information spreads is important because we're trying to reduce the spread of HIV information, reduce the spread of HIV. And so not only is the sampling algorithm and then using influence maximization able to reach more people, but is able to reach more people faster. We also looked at other metrics of HIV prevention. And again, here, condomless vaginal sex, you can see that the sampling algorithm leads to more of the population changing their behavior. And this is also done faster compared to degree centrality.
Beautiful way to kind of like marry this tech world with this social service world, like, and how we can kind of go deeper and impact young people and elevate them.
If this group became a really big thing, it can really help out a lot of youth.
So this is our collaborators is in Safe Place for Youth. I also wanted to highlight some recent work. I'm very excited by working with my friend, Professor Ravindran. This is work we had visited IIT Madras in spring of 2019, and we discussed the sampling problem. And Ravi and his team started collaborating with us on this RL approach to solve this problem. And so you can imagine that we start with a small, the current state of the graph, and then we choose the next node to explore. And if we have finished our query budget, if we have not exceeded our query budget, then we go back and query the next node. So this is a sampling policy that we are discovering. And the reward of the policy is the influence that that particular sampling is after sampling, choosing influence maximization nodes are able to spread. So this is work that was published at PAWS 2020, even nominated for the Best Paper Award. And so I'm just delighted that we were able to bring this collaboration together. And these are some of the results that are shown in terms of improvement over the algorithm that we actually deployed in our homeless shelters. So this RL algorithm is actually able to do better than what we have shown in practice. So this is very exciting. And hopefully this will be able to deploy and impact further more lives. Let me move on to a second topic. This is tuberculosis prevention, and this is work we are doing in Mumbai in India. And of course, TB, as you know, impacts 3 million people in India. 500,000 people die in India every year due to TB. And one of the challenge is non-adherence to TB treatment. So people are supposed to take this medicine for 6 months, but they drop off after some time. And this is not only problematic for themselves, but of course it creates drug-resistant bacteria. So the way to try to handle this is digital adherence tracking. So there's new kinds of technologies that are coming in. So you have here a sleeve as shown in the picture. So you open a pill and behind that is a phone number, and the patient is supposed to call the phone number every time they take that pill. Now this phone number is given at random, so the patient cannot guess it. And from checking who's called these phone numbers, you can figure out which patient is adhering to the medicine and who's not. So our challenge is, can we predict adherence of who's dropping off by looking at their phone call patterns? Specifically, earlier, the way to try to intervene with patients dropping off is to say, well, somebody has missed their phone calls for a while, and then the health worker can go and say, hey, you've been missing your pill taking. Can you please adhere to your medicine? Instead of doing this after they've missed taking a number of doses, can we ahead of time predict who's going to drop off? And if we can do that, then that will allow us to intervene earlier. So we have data for 1.5 million calls from 15,000 patients from Mumbai. Actually, it's within Mumbai, we got this data. This is with our collaborators, Everwell. And with this, we are trying to predict high-risk patients. So here's a picture. We have 4 patients here. The first one didn't call on day 1, called on the remaining 4 days. Second one called on day 1, day 2, but didn't call on day 3, called on day 4, didn't call on day 5. And you can see similar patterns for the remaining 2 patients. Can we predict in advance that these 2 patients, patients 2 and 4, are the high-risk patients, and the other 2 are going to go continue taking their medicine? Because if we can predict in advance that these are the 2 high-risk patients, then the health workers can intensify their attention on these 2 patients rather than spreading their attention on all 4. Of course, I've only shown 4 patients here. In reality, a health worker has to attend to hundreds of patients. So being able to isolate high-risk patients is actually quite crucial. And so we've been able to use this data, make predictions, and show that indeed we are much better at predicting actual, with increase the number of true positives in terms of predicting high-risk patients compared to a baseline approach that is used by Everwell, which is a simple rule-based approach, and reduce the number of false positives. So we are now waiting for IRB approvals in order to test this experiment, test our system in the field with Everwell. And hopefully this will allow ASHA workers in Mumbai to isolate high-risk patients and thus impact medication adherence. And so Bill Thies, who's a co-founder of Everwell, points out that this work has a lot of potential to save lives, and we are very delighted to be collaborating with Everwell. More recently, they've pointed out to us that there are these sleeves that are needed in order for the patients to call these random phone numbers, and those have not been manufactured. And so now the health workers are calling patients rather than the patients calling health workers. So what this leads to is we have a set of patients, and the health workers are going to call these patients every day to determine who to, and they can only call K of those N patients in order to figure out whether the patients are adhering to the medicine or not. You could imagine doing this in a round robin fashion. So if you have 200 patients, every day you call 10, and next day you call the next 10, and the next day you call next 10. But this is a very inefficient approach. Instead, we can cast this problem as a restless bandit problem, so that you can choose K patients to call every day by basically thinking of this as pulling K arms out of N. And more recently, we've completed this restless bandit model. Again, we are hoping that the algorithms that we have come up with could be tried out in Mumbai. We can show that this adherence monitoring problem cast in this restless bandit framework is indexable, which means that we can give performance guarantees and optimality of particular types of policies. I know that I'm running out of time, so I'm going to skip ahead here. We've been working, I saw earlier a presentation that talked about COVID-19 work. So we've built our own SEIR agent-based simulation. This was covered by Daily Beast in a more provocative way about our projections of how Georgia's lifting of the lockdown is going to work. This was just before the governor there lifted the lockdown. Obviously, this led to a lot of feedback to us from people in Georgia about how, pro and con. But one of the things I wanted to quickly share there is we've been looking at more detailed questions. For example, there are more sensitive tests for detecting COVID, and there are less sensitive tests. The less sensitive tests are very cheap. The more sensitive tests are more expensive. And so which test should universities run? Because students are going to come back And now universities are racing to figure out what is the right testing strategy. Should we test all of the students every day with the most expensive test possible, with the most sensitive test possible? Should we use a fast and cheap test? And so what we show is that with our agent-based model, that if you indeed do the fast and cheap test every 3 days versus say the more sensitive test, then clearly if you can run the more sensitive test every day, every 3 days that is, then it will lead to better results. But the more sensitive test is more expensive. So maybe you can't run it every 3 days. You have to run it a little bit slower. That means every 5 days or something like that. And so what we show is that if the more sensitive test cannot be run at the same frequency as the less sensitive test, it's not useful. If there's a delay in the result of the more sensitive test, again, it's not useful. So the message here is that universities may be better off just using this cheap and fast test. So let me now skip to the last part, which is work we are doing with wildlife conservation, and then I'll end and look forward to some questions. So this will just take 2 to 3 more minutes. I know I'm running out of time here. So this is work we've been doing in collaboration with World Wildlife Fund, Wildlife Conservation Society, and others. This is Uganda. This is Murchison Falls National Park. These are my videos from being there. These are snares or traps that are used to kill these animals. There's thousands of traps that are set every year to kill and maim these beautiful animals. And so here we are trying to predict the probability with which poachers may set traps in different parts of the park. So here we have taken the Queen Elizabeth National Park, divided up into 1 kilometer by 1 kilometer grid square. There's thousands of square kilometers of the park. So you can imagine this is a massive, massive set of grid squares. And now you're trying to predict where poachers are going to set traps, because there's only a small area where the poachers set traps. And so rangers cannot go to the entire park. They can only go to a small fraction of the park. So if you can give them where to look, that will help them remove the snares more effectively. So we have a data from 12 years of data, for example, from Uganda on range of patrol frequency in different parts of the park, animal density, distance to roads, rivers, area habitat, area slope, different features, and trying to predict where we are going to find snares. And we've been able to build a machine learning system called PAWS. We conducted detailed tests, for example, in Uganda, Queen Elizabeth and Murchison Falls. We selected 24 areas in each park and labeled some of them as being high risk and predicted some of them as being low risk. And we sent rangers out for 6 months. These were areas which had not been patrolled frequently before. So we are asking the rangers to go to new areas and find snares. And we find that where we predicted high risk, more snares were found. Where we predicted low risk, less snares were found. In Cambodia, these are my pictures from having been in Cambodia just last spring. You can find that numbers of snare captures after our algorithm was deployed went up 5-fold. This has been very exciting for us and for our collaborators in WCS and WWF. And so now in collaboration with SMART, which is a partnership of all these wildlife conservation organizations, we have integrated our PAWS system with the SMART system. And now the software is available. This is complete. This integration is complete. The software is now available for worldwide use. And in fact, as now the national parks around the world are beginning to start using this software to actually deploy in the field. So this is very exciting to see this being deployed, and hopefully data will start coming back so that we can do further research to improve protection of wildlife. So I'm going to skip this slide and just in summary, we have been focused on how to optimize limited intervention resources for public safety and security, conservation, and public health. We have looked at multi-agent systems and data to deployment pipeline, and in this way provided research contributions, whether it's in security games, game-focused learning, as you saw earlier, social networks, and others. I'll draw a few lessons in terms of future of AI for social good. First, key lesson, it is possible to simultaneously advance AI research and do social good. It is important to use a data to deployment perspective. We shouldn't just focus on improving algorithms, but the entire pipeline. It is important to step out of the lab and into the field, because that's where we really get to understand some of the key problems. It is important to embrace interdisciplinary work, whether it's with social work, with conservation and other scientists. And lack of data is the norm, a feature of many of these domains. It should be part of the project strategy and not just complain that, oh, there's not enough data, so we can't work in this domain. So with that, I'll stop. I'm looking forward to collaborating with people here. Obviously, I've begun collaboration with Professor Ravi and his students, but I look forward to other collaborations to realize AI's tremendous potential to improving society and fighting social injustice. So thank you very much, and I'll stop here.
Thank you so much, Milind. that was really inspiring, especially towards the end, like where you tied it all together in terms of the potential. So I picked up I picked up a question from the audience. I've kind of collated it in terms of one common theme, which is a recurring theme seems to be the question about generalizability. If a lot of the work that you alluded to seems to be very region specific, and talking about how to solve a problem in that space, then the data becomes very region specific, and the solutions become region specific. So, is there a good and a bad there, in the sense that the findings themselves are very helpful for the region, but how do you generalize that?
Right. So I guess I can take this question in different directions, and I'm not sure I completely understood the question, but you can imagine that so if you imagine something like homeless shelters or something of that type in Los Angeles, the challenges they face with respect to HIV prevention, this may not be the same challenge that some other homeless youth organizations may face in other parts of the world. But the basic problem that we have limited social worker resources, and somehow information has to be spread, is common. A concrete example is when we were talking to the central CTO, the chief TB officer in Mumbai, and her staff. They pointed out that one of the problems they face is how to spread information about tuberculosis prevention within the population in Mumbai, for example. And so the same social network idea of sampling a small social network and using that to figure out who are the influence maximizers could be useful in the TB context. And so whereas the problems are not identical, the techniques that have been discovered in one setting could be applied to other, because the central problem we face in all of these AI for social good domain is because of limited resources. So does that
absolutely, absolutely, which is that the common thread, it need not be the same data, and it need not be the same solutions, but there is proof that the way of analysis itself works, and so that is transferable, even if the data itself is not, or the solutions are not. I hope I got that answer correct.
Yeah.
So another question, Milind, is that this kind of work seems to be very different from a lot of what is touted and spoken about in terms of big data. There seems to be a lot of difference in the nature of the data and the algorithms itself, right? Like for one
yes.
thing, I definitely see that there's a heavier reliance on sequential versus one-shot approaches or scale by itself. But that's just one thing that I observed. Perhaps you could elaborate a little bit more on what does it mean to do data science in the real world, particularly with very limited data, and how does that translate to seeing differences in methodologies at a high satellite level?
That's a awesome question. I really appreciate it. So I must say that so we've been working with these organizations, whether it's wildlife conservation or homeless shelters or TB prevention or what have you, earlier with Coast Guard and so forth. And around me, everybody would keep saying, "Oh, this is the era of big data, and how much data, and we're swimming in data." And the school magazine would ask me about commenting on how AI is going in the era of big data. And I would keep looking at my data, and it is just not, this is not big data. But I'm still working with small amount, it's just not. And so So there are several, I mean, you can sort of think about different ways in which we can combat the fact that we have limited data. I showed you this idea of sampling a social network in order to try to gather the social network. We just don't have like Facebook scale, entire social network available to us. I think overall what this has meant is that we have to somehow rely more on sort of clever algorithmic techniques. So for example, when we talk about wildlife conservation, we are trying to figure out where to patrol based on predictions of where poachers have set their traps. So normally the way this would get done is you would first build a nice adversary model. If you have tons of data, you can really build an awesome adversary model and then solve a full game assuming this adversary model.
Yeah.
In reality, if you have limited data, your adversary model is poor. And so rather than taking a stage-by-stage approach or sort of assuming that each stage, the machine learning stage gets done in isolation, the game theory stage gets done in isolation, this limited data means you have to take more of an end-to-end approach. That means that the learning and the planning have to go together. I didn't get to talk about it much today, but basically the loss function in the machine learning is not accuracy, but actually it is how well would you do in placing rangers. So that way at least the learning is guided by what the task is at hand rather than just pure accuracy metrics.
And so, it's very aligned with a reinforcement learning paradigm, right?
Exactly.
And plan.
Exactly. And so it also means that now you can go back and say, if I only can collect limited amount of data, what data should I collect in order to perform well on my task? So you're kind of encouraged to take a more end-to-end perspective rather than taking each of these modules in isolation. But it's a great question. I mean, there's a lot more thinking that needs to be done. But yeah, I mean, in many of these domains, whether it's suicide prevention or something, some of the students who come in assuming, that they're going to do data science, they look at the data and they're horrified to see, well, the data is incomplete. It's not as much as they had hoped. It's not clean. There's a lot of inconsistencies, but that's what you got to deal with in these kinds of domains.
Okay, great. We have one more question from a panelist, Arun. Arun, if you could unmute yourself, please.
Hello?
Yes, we can hear you, Arun.
Yeah, I can't hear the question.
I heard his hello. Arun, we could hear you saying hello. Do you still want to ask the question?
I think there was Milind who said hello. So I think Arun.
Yeah.
Okay. Perhaps we are having a small difficulty, but I'm sure Arun will post his question on the Q&A, and perhaps Milind, there are some more questions in the Q&A that maybe if you could spend a few minutes and answer them, that would help a lot of our participants. So great. That brings us to the end of what has been 3 very intellectually stimulating days. And I'm really thankful for all the speakers who have given really exciting and interesting talks, and who have also been very involved with the whole process, ranging from the logistics and the testing and everything. So thanks a lot to all the speakers. Thank you to the participants. We've had a much higher number of registrations than we ever thought, 12,000, including both platforms, Zoom and YouTube. And along the way, you've been very engaged in both the Q&A and participation end-to-end in terms of involvement in the polls and everything and the feedback. So it's really good to see this kind of community around data science and AI and an interest in this area. We are passionate about it. It's great to see so many other people being passionate about it. as well. I just wanted to take a minute to just address one question that come up along the way. Often we've been asked in the forums as to how do people engage with RBCDSAI. The Robert Bosch Center for Data Science and AI at IIT Madras hosted this event. How do we engage with them if we are non-IITM? And we've actually had a lot of folks from industry as well as students. So I want to break that into two parts. So if you're from the industry, we engage with industry quite a bit. You can see many of our partners on our website. We do a good amount of training programs. We do industrial consulting, and we're really looking at something also more long term. We're going to be shortly launching the Industrial Consortium, which is a more long term engagement with industry where workshops and other forms of engagement are where we seamlessly integrate with industry research as well. If you're a student, a lot of students have approached us and saying, "Hey, I'm not in the IITM ecosystem. How do I plug into the center?" Again, I would really encourage you to visit our website. There is a Join Us page where we talk about a whole bunch of fellowships that are available for students, and you can avail of them. You can apply for them, and we look forward to you joining us in some form through that channel. And also a more organic channel is just simply that there are a lot of MS PhD programs in traditional departments at IIT Madras. So if you're graduating and considering, pursuing a master's or a PhD in your traditional department, as you might already know, RBCDSAI has close to about 30 faculty members across 10 departments. So if you work in the area of data science and are aligned with RBCDSAI faculty, you can avail of the center's resources and be a part of the broader community. So I invite a lot of you to consider that as an option as well. Okay, having said that, I will conclude and end the session with repeating my thank you. Thank you all. This has been very enjoyable, and look forward to engaging and collaborating with all of you in the future. Thank you.